All right, everyone, welcome to another episode of Robo Papers. Super glad today to have Jeremy Collins, one of the authors of this paper called AMPLIFY, Actionless Motion Priors for Robot Learning from Videos. Thank you so much for making the time, Jeremy. Maybe as a
Thanks
start,
for
if you
having.
can share a little bit about yourself, that'd be great.
Sure. Thanks for having me. I'm Jeremy Collins. I'm a third-year PhD student at Georgia Tech, working with AMPLIFY. I focus on deep learning for robotics, in particular, scaling data for robotics, alleviating the bottleneck. And in particular, recently I've been working more on learning from videos. So how do we utilize videos of humans to scale behavioral learning, essentially? So I'm here to present AMPLIFY, Actionless Motion Priors for Robot Learning from Videos. This is joint work with Laurent Cheng, and then co-authors are Kunal, Albert, and Benjamin, and the PI is Animesh Garg. So I'm going to start with motivation here. Scaling behavior cloning is expensive. There's been a lot of effort recently by some companies to scale data collection for robotics. One of the first companies to do this was Google with RT1 back in 2022, where they took 17 months with 13 robots to collect around 1,000 hours of video. And then a bit later on, the OpenX embodiment dataset came out in 2023, which was an aggregated source of datasets over the course of 5 years, totaling about 4,000 hours. And then last year, Physical Intelligence came out with Pi0, where they collected around 10,000 hours of robot videos or robot data over the course of 7 months or so. And then just a few weeks ago, the Toy Research Institute, where I was interning this summer, came out with large behavior models where they took around 10 months to collect 545 hours of demonstration data. So I think most people working in robot learning would agree that data is one key bottleneck. And an open question is how much data would be required for robots to generalize to new tasks and operate reliably in the real world. If we visualize these datasets I mentioned compared to some of the biggest or some of the most prominent large language models. So this is from Kevin Black from Physical Intelligence. He made this nice graphic comparing these data sets, assuming that humans read at, on average, 238 words a minute. You can kind of compare the timescales of text data sets with robotics data sets. And if you'll see, the robotics data sets really pale in comparison to these other data sets. And because we have this open question, we don't know if this bet is the right bet of collecting a bunch of robotics data, because it's going to take a lot of time and money and effort to get on the orders of magnitude that these language models are at. So I would like to ask this follow-up question. What other types of data can we learn from? And I would argue that there's a large reservoir of data looming in the distance, and that source of data is YouTube, which is around 1 billion hours of video, much of which contains humans doing tasks that we want the robots to do eventually. And one might imagine once we're at this point where we have generalist robots, they might be trained on this sort of data pyramid. So this is from Jen Fan. This is also analogous to Jan LeCun's LeCake, if you guys have heard of that, where we have some very large source of sort of self-supervised or unsupervised data. So this could be text and images and, of course, videos. And then toward the top of the pyramid, we'll have more of our on-task sort of data. So data on our embodiment we're going to be testing on and maybe on some of the same tasks. Okay. So that's kind of the motivation, and now I'll briefly go into prior work. I'll kind of go quickly through these slides, but feel free to stop me if you have questions. So lots of people have tried tackling the same issue of extracting action information from videos to benefit behavior cloning. Some categories of approaches are hand pose and object affordance mappings, representation learning with some sort of self-supervised objective, and also model-based methods where people might try and predict some notion of the future to inform the policy. Okay, so for the hand pose and object affordance mapping, there are several prominent works. One is Ego Mimic, where they estimate the 3D hand position, average hand position. There's also Whirl, which uses videos to determine object affordances, namely the contact location and the direction that it'll go afterward. I would argue that these have some drawbacks. They're quite limited in granularity because they use these abstractions that are quite low dimensional. So in the case of, say, Ego Mimic, it's literally a 3D state. Compare that with the tens of thousands of dimensions in an RGB image, or even more than that in a video. And then they also are imposing some constraining assumptions, in particular that they assume that all interaction happens with the hands and not the rest of the body. And then lastly, they're bottlenecked by these specialized hand detectors. If they fail, then their method might not get the right. Okay. And then we have this representation learning approach. One such approach is called VIP, which is a value implicit pre-training, where they have this contrastive style loss to have adjacent states be closer in this representation space, and then further states in time be further away, and they sort of learn this value function this way. And there's some follow-up working kind of inspired by this from Sergey Levine's lab called ICVF, which we can get into, but I'm going to kind of gloss over that. And then a recent prominent work that's kind of been scaled up is called LAPA, where they take these frames at time t and time t plus h, and they learn this discrete latent action that sort of predicts the transformation from the frame at time t to the frame at time t plus h. Okay, yeah, and then I guess I didn't get to the limitations of this, but the limitations are varied in this. I'll focus on maybe LAPA here. Here they focus on pixel space prediction, which might contain task irrelevant features. And it could also be quite computationally expensive to predict this high dimensional RGB data. All right, and then lastly, we have these model-based methods. I'll go over ones in particular that are predicting videos. There's UniPy, which has this video prediction model, and then they train separately this inverse dynamics model that goes from pixels to actions. There's the Cosmos model from NVIDIA, where they have two types of models. They have this action condition video generation model, and then they have this text condition video generation model, and they also train this inverse dynamics type of thing. You can also do like model-based RL with this approach. However, this kind of approach is really computationally demanding, and like I alluded to before, it's quite expensive to predict RGB directly, and it might capture task irrelevant features. And in this work, we're going to be focusing on instead of RGB data, movement happening inherently in the video. Okay, so that's most of the prior work there. Now I'm going to ask, how do we, in this work, extract action information from videos? And we choose point tracks as a common abstraction between human videos and robot demonstrations. So there's lots of recent work that sort of make these networks to track points in videos. So the input here is some initial location in the video, and then the output is how those locations evolve over time throughout the entire video. So you'll see here it's quite robust to occlusion and the camera movement as well. So what we'll be doing is using this as ground truth. So here you'll see the ground truth for our approach, what it's going to be here, which we have this uniform grid of 20 by 20 points, and then you'll see how they're moving within the next second or so. Great. And an advantage of this representation is that it captures fine-grained seed dynamics and doesn't have the sort of rigid body constraints. Say if you were to model object poses, you'd have sort of constraints on what types of objects you can interact with. Point tracks have no such limitation.
So unlike in the previous video, you're predicting like everything in the background as well, and you just predict that they are not going to move. Is that the?
Yes.
Okay.
Yep, exactly. So
Okay.
Most of the predictions are going to be zeros. However, we do this in a way that's computationally efficient. We can get into that in a bit, but we sort of have this task agnostic dynamics prediction.
That make it hard to do if the scene was like really noisy or complicated, like if there was a lot of background distractions, or?
Yeah. So I think this is maybe a data question. If you have a bunch of distractions in your data, and you could learn to be robust to them if your model can kind of grok what's relevant to the task and what's not relevant to the task.
Yeah, makes sense.
Yeah, I have a quick question. I don't know whether you're going to address it later, but like I wonder, like if you're just doing point tracks naively, like how do you determine the causality? Like what if it's the cloth that is moving the arm?
Yeah, it's a good question. Yeah, there's this question of correlation versus causation. If you see the cloth move, is that your action space, or is your action space the arm? I would say this is also ambiguous in everyday tasks. If you're using a spatula or something, is your spatula the end effector, or is your hand the end effector? It's kind of hard to, there's not really a clean delineation between the agent and the environment in a lot of cases.
I see. Okay, got it. Yep.
Yeah, cool. Another advantage of point tracks is that they can potentially share information across embodiments. Here's a work from Roshi Liu and Alper Camberg, where they have this demo where they can retarget hand motion to robot hand motion using some notion of distance, like minimizing the distance in point track space. Another advantage is that the point tracks are not tied inherently to the visual features, so that they can kind of change as long as the point tracking model is working. So
does this work well? Does this work well if you're like moving directly towards or away from the camera? Because I'm curious if there would be any issues with that.
Yeah, I think camera movement. Well, so do you mean depth ambiguity? Is that kind of what you're getting at?
I guess both. Yeah. So like camera movement, of course, is important, but like here, but so far all the tasks you've seen of it. I mean, obviously for illustrating the concept, it's much clearer to see something moving back and forth laterally. But like, do you have any issues with like predicting policies that are moving directly forward or away from the camera because of depth ambiguity? Or
so for our approach, we're usually using multi-view RGB when we're like rolling stuff out on the robot.
Makes sense.
So that's how we tackle that. But you're right, there is some depth ambiguity. I would argue this is less of a problem when you're talking about motion, because say when you're moving your hand away, all the points kind of shrink and become closer to each other.
So you're predicting lots of points, so it becomes obvious, I guess, that they're okay.
Yeah, I think it's still
yeah.
somewhat ambiguous, and it's like a weakness
Okay.
of RGB data in general.
Yeah. So I guess maybe this is too early and you're getting into this, but you said, but since you're doing multiple cameras, that means, are you also predicting correspondence across cameras?
Yeah, so we don't predict correspondence. Our argument
You
is
don't
that
need
since
to?
we're predicting
Okay.
these dense motion grids, grids motion, then
fair enough.
there will be inherently lots of overlap between them. Because in the ideal case, when you track every single pixel, if those pixels are common between viewpoints, then you're implicitly capturing the 3D trajectory.
Yeah, that makes sense.
Cool. And then now I'll try and make a more sort of first principles argument here. So I'm going to argue here that point tracks have a direct mapping to the physical world. What is a video? A video is a way of capturing the distribution of amplitude and frequencies of photons hitting this array of photodiodes. And each of those amplitudes and frequencies and distribution of frequencies, they correspond to a 3D point in the world. And what we're essentially doing is taking this 3D point, measuring some qualities of that point, and then projecting it onto this. And then similarly, I'll ask the question, what is an action? Typically in robotics, or in behavior cloning, we parameterize actions as delta gripper poses. Those poses consist of positions and translations and rotations. The translations can be captured by a single point on the gripper and tracking its movement in 3D space. The rotation can be captured with a set of at least 3 points and seeing how that plane constructed by the 3 points moves between adjacent times. So our intuition for this work is that a video is a dense representation of dynamics, as we're capturing densely in space and time all of these shooting projections of 3D points. And then a robot action is a subset of these dynamics captured by the video. Great. So now that we've introduced point tracking as a common abstraction between human videos and robot demonstrations, I'll talk about just a couple of representative works that use these as a common abstraction. So first, there's ATM, any-point trajectory modeling. So it was the first to use point tracks for policy learning. What they do is they essentially turn each point that's being tracked into its own token, or it's a bit more complicated than that, but we can think about it this way. And then they train this dynamics model to predict the future evolution of the points, similarly to us, but they predict explicitly in pixel space. One downside of this is that it's computationally intensive, so it takes 4 A100s, 5 days just to train their behavior cloning setup. I don't know how much it is for their actual their actual track model. Another downside is that they only evaluate in distribution settings, so they don't show any sort of generalization beyond tasks for which they have. And then we have tracked act, which uses a diffusion model to predict how this grid of points is going to move. So one upside is that they see generalization to unseen objects and scenes, but then the biggest downside is that they require a goal image, and then for their policy they assume rigid body transformations, and they have just this like post-grasp policy. All right, and then lastly, almost done with my work. Lastly, we have GenDAct, where they use pre-trained video generation models, video generation models. And they take the point tracks both from the robots and from the generated human videos to condition a policy. So their policy cross-attends to both of these tracks. However, they require video generation at test time, which is quite a bottleneck. You can only have so high of a frequency for your policy's inference. Okay, so that's it for prior work. Now we'll get into
the most thorough prior work that we've ever had on this podcast. So,
this is really great, man. Thanks for all the reference to all the prior work. It really set the stage. Okay,
yeah,
so what's your
I
insight?
feel like I need to give credit where it's due. Yeah. Okay, so now let's get into Amplify itself. So what we do is we decompose policy learning into a 2-stage approach, where our intermediate representation is latent key point motion. So our first module is this forward dynamics model that learns to predict a sequence of latent motion tokens given the current observation and task. And then we have an inverse dynamics model that takes these latent motion tokens to condition a policy. One advantage of breaking down policy learning into these two components is that we can leverage different types of data. So typically with behavioral cloning, you can only train on demonstration data, but by decomposing policy learning into these two components, we can now train on video data for the forward dynamics model and off-task or play data for the inverse dynamics model. So we can leverage all 3 types of data here: text annotated video data, demonstration data, and off-task. Great. So here's a high-level overview. So again, behavior cloning can only take demonstration data, whereas Amplify, what we do is we decompose policy learning into this forward dynamics model and this inverse dynamics. Okay, cool. So that's the overview. Now we'll get into the actual algorithm. So our algorithm has 3 steps. First, we'll talk about motion tokenization. So we start with a video chunk. This is just about 1 second of video, and then we'll pass this second of video into a point tracking model, namely CoTracker 3 is what we use. And we preprocess all of the data this way. And this visualization you're seeing of the point tracks, these are just the moving points. So all the non-moving points we're just not visualizing for illustrative purposes. Okay, now that we've pre-processed these key point tracks, what we do is take the single step velocities. So we take the difference between adjacent time steps to get the instantaneous velocities for each time step. So we have 16 points being tracked throughout this 20 by 20 grid, and then each one we take the difference between t+1 and t to get these velocities.
And these are the velocities like in the XY image plane, right? Not the
Exactly.
Yeah.
Yeah, in pixel space. That's right. Okay. So these velocities become inputs to a causal transformer encoder, which we then take the outputs there of this transformer encoder and we discretize them with finite scalar quantization to produce these latent motion tokens. These are discrete tokens that model the velocities of all the points. And then we decode with a transformer decoder with no masking. And so this is probably the hardest part to understand here is what we actually train this VAE on for motion tokenization. So I'll break it down here. So we have this transformer decoder that takes in the latent motion tokens, and we then for each point and for each time step, we model the probability distribution in this local window, around each of the points, and we model the probability distribution of the relative motion of each point for each time step. So for example, say we take the point at the top right corner at the 0th time step. So say that's this point, that's the center of this grid. And then we perform this classification task where the ground truth is the instantaneous motion. So in the next time step, where's the next pixel going to move relative to the current pixel? And so we use that as the ground truth, like a one-hot encoding at that point. And then we train with cross entropy. So what this does is probabilistically models the motion of every single point for every single time step. And the reason this is advantageous is because we can now capture multimodal distributions of the pixel space motion. So prior work has all done simply just regression in pixel trajectory space. However, if you'll actually visualize the distributions in the data, most of it is quite multimodal for the reason that a lot of points don't move. So you'll end up having a peak here at 0 and then another peak here at the actual sort of ground truth. And if you regress this, then you'll actually take the mean of these two modes of the distribution, which will end up underestimating the motion in the video.
If it's just bimodal, why not just like classify whether or not a pixel is going to move and then regress?
That's a reasonable thing to do. We tried several things. We tried kind of like upweighting the 0 class. We tried doing Gaussian mixture models and stuff. But what ends up working the best is just modeling the actual distribution. So when we visualize our predictions, we actually have to do some additional computation on this. So we have to take the argmax of this distribution, and then we have to take, so once we have the argmax, now we have the instantaneous velocity of a given point at a given time step. Okay, and then if we have all the velocities to get the tracks back out, we have to take the cumulative sum of all the tracks. Okay. So this is the first step. This is how we tokenize motion into this latent motion space. Great. So now that we have our latent motion tokens, we can train a separate model to predict them. So this is our forward dynamics model. So we'll take these outputs of the motion tokenizer, and we'll use them as ground truth for an autoregressive transformer. So we have the inputs of the forward dynamics model here. We have the tokenized text and the tokenized image. We'll then append a starter sequence token, and then we'll pass those things into an autoregressive transformer. And what this is doing is it's predicting these discrete tokens. So it's predicting the indices in our codebook. And we'll use, like I said, the output of the motion tokenizer as ground truth. So we just apply cross entropy again, but in this codebook space instead. Any questions about this part?
Okay, actually, I had a question about the previous one that I thought of. So this was on the tokenization. I was just wondering, because you had this one thing. You say that you take the velocity corresponding to the highest probability class. So you don't need to do anything to account for the fact that it's a distribution here. Does that lead to any issues if you have like something that's 50-50 bimodal, or like it could move left or right? I don't know what that would actually look like.
Yeah, so this is something we tried too. When you're decoding, You could do different types of things. You could take the argmax, or you can do something like top K sampling, nucleus sampling. The issue there is that because you're sampling independently per key point, per time step, there's no constraint for the predictions to be consistent between points.
Gotcha. Okay.
Does that make sense? You might get points going in different directions, and what happens in aggregate is it takes kind of the average motion now.
Okay, that makes sense. All right. Yeah. Cool. Okay.
Good question though. Great. Okay. Yeah. So like I said, we have this autoregressive transformer that predicts the discrete latent motion tokens. Okay. So this enables us to predict these tokens without the ground truth key point trajectories, because otherwise we would need them to get this. Okay. So now we have our predicted latent motion, and now what we're going to do is condition a policy on it. So we'll pass these latent motion tokens in along with proprioception token and an image token, and we'll cross attend to them with this decoder transformer. So we start with these learned queries. These learned queries attend to all this conditioning information, and then they'll output an action chunk. So yeah, this is the whole system. So this will kind of wrap up the method. I'll kind of leave it here for a few seconds in case there are any clarifying questions. I'll go through it at a high level, and then I'll move on to experiments. So we have motion tokenization, where we compress these key point trajectories into this discrete, compact, latent motion token space, which we learned from modeling the distribution of motion for each point, for each time step. Okay, so that allowed us to learn this sort of latent action space almost, which we then learned to predict given just the current observation and the task description. And then now that we've predicted it, we can feed it into a policy. Okay, yeah, so we perform experiments on 3 different data sets. Firstly, we have Libero, which is a pretty common data set to use these days in robot learning, which has 6,500 demos with 130 tasks. So 50 demonstrations for each of the 30 tasks. We also have something v2, which is a data set of 220,000 captioned human videos. And then lastly, we have Bridge Data v2, which has 60,000 demos, 13 skills with a single embodiment. And we ask these research questions. So firstly, how does Amplify perform on point track prediction? And then when we condition a policy on these latent motion tokens, how do we perform these different behavioral cloning setups, like full behavioral cloning versus few shot, and then also zero shot task generalization settings. And then lastly, we ask, can we bridge the embodiment gap and benefit from human data? Okay, so Amplify achieves state-of-the-art point track prediction performance on all 3 of these data sets and by all metrics that we use. So we compare with ATM and Track to Act, which I alluded to before. And then we also have this baseline called a SEER, which is a video prediction model. And then we track the points on the predicted videos to get our point track predictions. And we find all across the board that we do the best on tracking the C. And then there's also this delta AUC metric, which we can get into if we want, and also pixel-wise accuracy, which is how often we get the exact correct pixel for the pixel space motion. Okay, and then we have some nice visualizations on the bridge data set here. Again, I'll rehash the motion that you're seeing, or these like point tracks that you're seeing, are just the moving ones. Our model is predicting that the rest of these and this like 20 by 20 grid are not moving, and we're just not visualizing those so that the image is not.
Looks nice. I really like the visualizations. Go ahead. Sorry, Michael.
Yeah, sorry, I have a question. So maybe I'm missing something. So for example, on the top left, right, when the robotic arm is trying to open the toy oven door, the motion on the oven door it seems that it's not, there's no like tracking over there.
Yeah, I think for this prediction, for this like smaller motion, the initial pull on the door, it's not modeled completely correctly. For this like second larger motion, you kind of see some of it it's modeled, but yeah, you're right. It's not perfect.
Oh, I see. So I think similar, I think the bottom left when it's pulling out the drawer, I was kind of expecting maybe to also see something on the drawer itself.
Yeah. You're right. It's
also,
sometimes it misses the finer grained motions. It ends up being better in our smaller data sets. But yeah, I do suspect if we threw more compute at this, we're a bit compute loaded in academia, but if we train this with more GPUs for more time, I suspect that it would model these finer grained things. Yeah. But yeah, it's a good point.
Yeah, like the door is bigger, right? Shouldn't that be more of your loss?
Yeah, well, this is fair. You can ask the question of like, what motion happens for what amount of time? Like, how much motion happens in pixel space and for how many time steps? I think our model ends up modeling the larger motions first, and then I think eventually this would happen, but yeah, not this time.
Yeah, I was going to ask, is it because like, let's say, the window here is roughly 1 second, but because the arm has been moving the first, let's say 200 millisecond, and then you just attend to that first, and then it just continue to attend to it. And so because the drawer, those 2 drawers only move maybe like half a second in, I don't know whether that could be the reason.
Yeah, I think so. And this is an implicit bias of the model, I'd say, because if you're modeling pixel space motion, the model is going to care most about the greatest magnitude motion in pixel space, whereas we should actually be caring about something different. We should care about the motion of task relevant objects. So yeah, I think it could be advantageous to impose this bias on the model. This is something that we did try early on, but we were actually bottlenecked by the quality of the text conditioned segmentation models. Maybe those are better these days. We tried that like a year ago. I think it's a fruitful direction since it would allow more efficient learning of the task relevant motions.
Got it. Cool. Well, but it's already SOTA point tracking like performance. So
yeah, still, if you were to look at ATM or Track to Act on these videos, I doubt it would be the same quality.
Got it.
Cool. And then now we actually look into the policy learning side of things. So this, I would say, is not actually our sort of target setting because we have plentiful action data. So for this setting, we have 50 demonstrations per task and also 50 videos per task. So the point of this is just showing that we're on par with some of these state-of-the-art methods, but we're not decisively state-of-the-art on this setting. So we compare with diffusion policy and Quest and Baku, and then also Amplify without without conditioning on the latent motion tokens. And then for the models that use video pre-training, we look at UniPy, which I mentioned before. It does this video prediction objective and then trains an inverse dynamics model condition on the predicted videos. And then we have ATM, which also uses point track motion. And you'll see some of the movements here. For here, it does actually get the movement of the drawer, luckily, and of the microwave here.
But is it good or bad if it gets the movement of the door? Because I would imagine, I actually was assuming it was good that it didn't, because wouldn't that hurt generalization if you tried to do it on any scene?
I don't know. I feel like both are important. Especially if you're trying to do cross embodiment learning. Like say, if you have a human video doing the same task, it'll actually have, exact. It should be pretty close to exactly the same motion in the drawer, whereas they might differ a little bit in the dynamics of the actual of the agent itself.
So it's certainly for the point tracking, for the conditioned policy part, like if the input was a bunch of points moving that it hadn't seen before, wouldn't that hurt the performance? Or maybe not. I don't know.
I would say that what prevents this from hurting performance is conditioning on the image. Okay. So the policy can still have full context by viewing the image and how the points correspond to the places in the observation.
Okay, makes sense.
Great. Okay, and then now we have this few shot setting. So the setup here is that this is still Libero, but we start withholding the action information and training on all of the videos. So for all three of these graphs, we train on all 50 all 50 videos from the demonstrations for Libero. But then say in this left graph here, we only provide 2 action trajectories out of the 50. So these success rates are gotten with only 2 demonstrations in action space, whereas the rest of the 48 are provided just in pixel space. And we compare with ATM and then this ablation where we don't condition the policy on latent motion. And as you'll see here, we handily outperform ATM. I think it's around 2x on average for the 2 demo setting. But yeah, I think it's quite cool. It kind of shows you that RGB data has sufficient information to back out the actions, which I think is quite.
Yeah, but it seems that so the delta from 2 demos to 10 demos is not that big anyway. So you already get a lot from just learning the latent motion just from RGB, and maybe just 2 so-called demo, and you get quite good already.
Yes. Yeah, I think this shows that the inverse dynamics model or the policy is quite good at mapping pixel space motion to actions.
But just to double tap on that, like these 50 demos is basically same scene, same task, right? So
yes. So there are several different subsets of Libero. And we when we hold out the action information, we have how do I phrase this? So we just have the 2 demos per tasks. Mm-hmm. Each of these have 10 tasks, except for Libero 90, which has 90 tasks. So for each task, we withhold 48 of the 50 demos.
Got it.
So it's still sort of in distribution in some sense.
Got it. I'm just trying to wonder, maybe this is, you're going to talk about it later. So, but coming back to, let's say, the YouTube example, right? YouTube, you don't have, let's say, 50 probably demonstration, it's purely video of the same scene, similar task. Mm-hmm. How do you think that will translate?
Yeah, it's a great question. I think this gets at the core of why we should be training generalist models. The reason being, the more tasks you train on, hopefully the fewer demos you need per task. I would say this was a key finding of the large behavior models paper, where this was kind of rigorously shown. So my best guess is that if you were to train on tens of thousands of tasks as opposed to 10 tasks, you would need much fewer than 50 demos to sufficiently learn that.
I see.
Yeah, so before we get to the human videos, I want to have this go through this last experiment we did in Libero. So I would say this is our most challenging setting. The setup here is that we train on the videos from all subsets of Libero. So we have the videos from Libero 90, Libero long, object, spatial, and goal. So we train our 4 dynamics model on all of it. But then the inverse dynamics model, we train only on Libero 90. So the only action information we ever see is from Libero 90. And then our evaluation setting are all of the tasks where we only see pixels and not actions.
All right, sorry. What's Libero 90? I think I just missed this one in grad school. So what is
No worries.
it came out after. All right.
So Libero 90 is a set of 90 varied tasks where they're all around the same horizon as object spatial goal, but Libero Long has longer horizon. So I think they're around 200 time steps on the order of 10 to 15 seconds. Yeah, so just a variety of 90 tasks.
Okay.
And
this is a non-overlapping set. So you have long
Right.
object spatial, which are all different tasks that you so you trained on, I guess 400 tasks and tested on 90 held out tasks roughly. Is that right?
So we train on there are 130 tasks.
I'm guessing the
total.
numbers.
No worries. So there are 130 tasks total.
Okay.
In this setting, we train the video, like the point track prediction, on all 130 tasks, but then we train the inverse dynamics model on only the 90 tasks in Libero 90. And then we evaluate in the held out tasks where our inverse dynamics model has never seen the actions. So all of these results here you're seeing are evaluated on settings where we have no action data, only pixels. Does that make sense? So this is sort of this task generalization setup. And the key question is, can we extract action information from pixels alone? And I think the answer is yes. We get performance nearly on par with our behavior cloning results in this setting, which demonstrates that our inverse dynamics model sufficiently learns this general mapping from motion to action, from pixel space motion to action. And then at the bottom, you're seeing rollouts in these held out settings.
Okay. And I know you had the numbers and stuff on the previous slide, but how much of a difference do you get between this and when you actually trained on these held out tasks?
If you actually train on all the held out tasks, it gets pretty similar performance to the.
Pretty similar.
Yeah, there's an incremental benefit, I think, from the BC thing if you were to train on everything.
Okay, great.
Imagine a couple percentage points higher than these.
There's a couple percentage points. It's not massive, right? So that means that it was really generalizing very well. That's nice.
Yeah, great. Okay,
all right,
cool.
Awesome.
So now we can get to the human videos. So at the bottom, you'll see the human demonstrations that my co-authors and I collected. And then at the top, you'll see the resulting rollouts from our policy. So the setup here was we trained our model on approximately 50 demonstrations from humans, and then around only 10 demonstrations from the robot. And we have diffusion policy as a baseline, and then the actual policy rolling out here for our method is just diffusion policy condition on the latent motion tokens. So we try to keep everything the same except for the latent motion tokens. Cool, and you'll see we have a pretty decent benefit. I think it's around 35 or 40% improvement in success rate on average, and we see on average a better performance improvement from the more complex tasks. So namely these two tasks on the left, this cup stacking task and this opening the box and then the pick and place. We see most of the benefit from that, and then we still see a little bit of benefit in this simpler pick and place task.
Sorry, Jeremy. So when you say, let's say, for example, 5 demos, you mean 5 human video demos? Is that what it means here, or?
Yeah, so we collect 50 human demos and then around 10 robot demos per task.
So there are actual, I see.
Yeah, and so diffusion policy is trained just on the 10 robot demonstrations because it can only be trained on demo data.
Mm-hmm.
And then AMPLIFY, we train on those same 10 demonstrations, but we also train the point tracking model on the 4 dynamics model. We train it on the human videos too.
So what you're saying here is that the human videos help to augment those the demo data, basically.
Yes, exactly. Yeah.
Okay, but you still need the. Okay, got it. Okay, sorry. Yeah.
No worries. Okay. Yes, and then lastly, we perform this small experiment where we try conditioning a video generation model on our predicted tracks from the 4 dynamics model, and we show that there's a marginal but meaningful improvement in performance when we condition the video generation model on the predicted tracks.
So these are literally like Gen AI kind of model. Like
what's that?
These video prediction models. These are like just video generated like for a few frames forward, and then you do the tracking to do. Sorry, the video prediction models here. Those are the ones you're talking about, right?
Yeah. So there's this off-the-shelf video prediction model called AVDC that's conditioned on the first frame of the video, mm-hmm. And then we add the latent motion tokens to the text conditioning as a thing to condition on. And the intuition here is maybe that the video generation model learns to become more consistent with the motion when it's trained explicitly on this pixel space motion.
Okay. So also basically, except for the first frame here, everything is generated, right?
That's right. Yeah, these are all generated videos. And this is on a single GPU for like overnight.
Is that true of the whole project, basically? Single GPU kind of scale?
Pretty much. Actually, none of our training runs had more than one GPU. And we trained for at most maybe 3 days for the Libra 90 stuff.
Do
So
you
I
think
it's
you'd
much
see any
faster to
cross-domain
train.
transfer? Like if you trained on Libro 90 and then tried on one of these other tasks?
We never actually tried mixing between the datasets. I think that's advantageous. We just never really got to the point where we had this like common data loading scheme for all of them. But I think it makes sense. You probably see some transfer at some point. Okay, great. So then lastly, I'll talk about limitations and future directions. So the biggest limitation of Amplify is that it doesn't model camera motion very well. So you'll see our predictions from something v2 down here. And because the majority of the motion in these and the ground truth is going to be from the camera, that's what our model will capture as well. And so even though sometimes you'll see some motion on the hands, the majority of it's going to be of the camera movement. So I think there needs to be some sort of way to either explicitly predict that and then sort of have two different predictions, one of the camera motion and then one of the agent motion. Or you can maybe condition on it once it's been predicted. Condition on the camera motion once it's been predicted. Yeah, and then for future directions, I think it's useful to explicitly model the 3D motion of the agent in the environment. I think we could also look at scaling up Amplify by swapping out the Ford Dynamics model, which was trained from scratch, swapping that out for a VLM, and potentially using these discrete latent motion tokens and the vocabulary of this VLM. And then lastly, potentially, it might be more scalable to have a fully learned latent action representation in place of this explicit pixel space motion rep.
Sorry, could you elaborate? What do you mean fully learned versus?
Yes. So the idea is, imagine instead of compressing the point tracks, we compress just the entire video.
I see.
So just fully end to end instead of this abstraction that we kind of hard coded ourselves.
Yeah, but that could be the reason that you have at least that the performance that you are having now, because you picked the right maybe representation for.
You think that could be the reason for?
Yeah, I mean, I'm not sure whether like just by fully learned like it necessarily means better.
Yeah, maybe that's true. I do suspect at some point we'll be faced with the bitter lesson of at one point is pixel space motion not enough to model some complex tasks if it's maybe dexterous manipulation or something like that. Yeah. Cool. Okay. Well, that's it for the presentation itself. I'd like to again thank Laurent, my co-first author, as well as my co-authors, Kunal and Albert, and then my advisor, Animesh Gard.
Oh. Yeah, very cool. Yeah, I got a couple of like follow-up questions, I guess. Like, so it seems to me that like in this, I mean, given the limitations, but at least if the camera is in a fixed position, this will already work quite well, right? And especially if you can just augment with a lot of human videos. Obviously, human videos is a lot easier to get than actual robot demo. I don't know. It's that is the conclusion you have, right?
Yeah, but there's still a long ways to go. You know, if you look at natural videos on YouTube, almost all of it has like pretty drastic camera motion.
Yeah,
so we need ways to sort of get beyond that. I think still early days.
Well, so I'm not thinking about YouTube. I'm just thinking about like, okay, let's say, you limit your environment or the condition is that it's a fixed camera. How many more human video like do you need? Or let's say if you collect more, like you mentioned just now, like was that like 50 human videos on top of the 10, right? What if you do 100 human video? Like is it gonna do better or what do you think?
Yeah, I think we don't have concrete evidence for this yet, but I do suspect that this scales. One could imagine a human as just another embodiment, and even if you want, you could back out actions if you want. Like I said, some prior work models the hand pose. You could have delta hand pose be the action space, and then really what's the difference? I mean, maybe you have some more error on the hand pose, but I think fundamentally there's not much of a difference between watching a human and watching a robot do a task. If you believe in this whole cross embodiment thing, if you train on a bunch of robots, then you'll get better performance. Then why not have N+1 embodiments where the N+1st embodiment is the human? And we don't know yet how many human demos or robot demos worth, but I do think that the relationship's monotonic. If you collect orders of magnitude more human demonstrations, I don't think your success rate will go down, and I don't think your generalization capabilities will get worse.
Right.
So I think at some scale it's going to be
or maybe like out of those so-called 50 human videos, you ask the human to, I don't know, maybe half of it, 25 of them use the hands, the other half you use the chopstick. Is another so-called embodiment. But since you're only tracing and tool use is another cool thing.
because there should be much less of an embodiment gap, right? If a robot's using the chopsticks versus a human using the chopsticks, you probably have similar strategies. I mean, maybe slightly different affordances with like grip strength or something, but I think the tasks will be achieved in similar. So that's a fruitful direction for anyone looking to learn from videos, I think, is looking at the tool use.
Yeah, great.
What was your sense about all these like maybe egocentric video like from smart glasses? Do you think those would be particularly helpful for, especially for humanoid deployment? I mean, half the time you show the hands and then the hands is doing stuff. Do you think this will apply
I
well?
think
Although the smart glasses is used moving all the time though.
It's true, but I think there are ways to get beyond the camera movement. And I do think that this is going to be quite useful. It probably depends on how much this scales in terms of how many people are going to be willing to wear the smart glasses. How much do you need to pay them, and like how many people can you convince to wear smart glasses, and can you get a variety of tasks this way? There's a company doing this in China for factories, which is great.
Yeah.
Like you'll get a lot of data this way, but I'm not convinced that you'll have a huge amount of variety. So can you convince people in their everyday lives to film themselves doing the dishes and whatnot? Obviously there are privacy concerns and stuff. Maybe, but it depends on both the scale of deployment and also the scale that's sufficient for enabling task generalization for robots. Right?
You have to resolve that one huge issue, the 3D perception, right? Or the decoupling camera motion, which I guess becomes much easier with 3D. So maybe you don't need to really solve 3D.
There are some great off-the-shelf networks. There's VGGT, which can estimate camera poses quite well, given a video. There's also a Cuter and Monster and all these other like Blake 3R papers. It seems like, at least from the demos that they show on the websites and whatnot, it seems like they work quite well at going from videos to camera poses. I have tested some of these, and my colleagues and I have tested these on robot videos, and it's not quite as good, but it's getting there. So I think this sort of like pseudo-labeled camera pose will be pretty useful.
It seems like a tractable problem, but I definitely agree. So why do you think they're not as good yet? I guess this is kind of out of the scope of the paper, but
no, it's fine. I think a lot of time there's just limited information, especially about say like camera intrinsics. You don't always have that sort of metadata.
So you think it's kind of out of distribution, basically, or like
I don't know. I think sometimes there's just like it is an under-constrained problem in some sense.
Sure.
I do think if you had perfect intrinsics, in particular, like the distortion of the camera and the focal length, if you knew these things, it would be unambiguous. But because all of this internet scale data sort of doesn't specify these things, I think there might inherently be some noise, which maybe that is arbitrarized by the scale of the data. But yeah, I don't know. That's my best guess, but I'm not an expert in this.
Yeah, makes sense.
And I also wanted to get another point. So you mentioned these like ARIA glasses type, or smart glasses type approaches that collect data from the bottom up. I think there's also merit in collecting data from the top down. I maybe won't specify. So I'm thinking about this quite deeply right now, but I maybe won't specify specifics. But I do think scraping the internet for videos is quite a fruitful direction. Even though it's quite messy, you might be able to get orders of magnitude more data than you would from collecting data from the bottom up. So I think it's worth kind of throwing our models into the deep end at some point and just training them on all the messy data. It's worked in the past for other fields of AI. I don't see why it couldn't work for learning from videos.
Yeah, I guess in general, if you can afford to compute, you can throw more data into the thing.
Yeah.
Right.
Yeah. Okay, awesome. Well, yeah, maybe, since we're wrapping things up, we always ask this same question, last question. Are there any like papers that you come across recently? It doesn't have to be directly related to, this work that really like blew your mind or like, inspired you, if you want to give a shout out.
Sure. The first one that comes to mind is the AGIBot Colossus paper. They have this setup where they train a behavior coding model on, first they predict latent actions with kind of something similar to LAPA, and then condition on that they predict low-level actions. I think this sort of opened my mind to this maybe future paradigm where we have like high-level predictions first, and then we go condition on the high-level predictions, we make low-level predictions. I know there's work on this in sort of like a text space if you're kind of reasoning on your models. By that, I mean you have a high-level task description, and then you break it down into subtasks, and then condition on the subtasks. Sort of this system 1, system 2 setup. But I'm imagining something maybe broader, which is inspired by this, which is you have this whole sequence of tokens you're predicting, but the granularity slowly gets finer and finer as you auto-aggressively predict more of them. You can imagine you have like an observation and then a high-level task description. And then, like I said, you break it down into subtasks. And maybe a condition on that, you predict latent actions or maybe even some other abstractions like bounding boxes or object segmentation, those kinds of things. and then condition on all that high-level info, predicting the low-level robot actions. I really like the idea of that sort of paradigm, and the AGI about Colossus paper is the one that kind of maybe see that structure.
Yeah, I think that data set is also one of the largest of its kind. So, yeah,
and it's
we should try
becoming
to
more
get those
popular
guys
to
on.
use.
Yeah. I
Absolutely.
think it's
They're doing good
kudos
work.
to them for open sourcing. Awesome.
Yeah.
Yeah. All right. Yeah. Thank you so
Awesome.
much, Jeremy. Thanks for all the sharing. Yeah. Looking forward to your next
Yeah.
paper.